Okay, let's jump right into it. Picture yourself in a crowd, maybe at a huge concert,
Yeah.
a really busy pilgrimage, or even like a sudden emergency evacuation.
Yeah.
Not just any crowd, but one so dense you're literally shoulder to shoulder, maybe 5, 6, or even 8 people packed into a single square meter.
Hmm.
That feeling of being in an overwhelming, unpredictable mass where individual movement is almost impossible. It's intense, right?
And that intensity carries a real danger. I mean, at these extremely high densities, something fundamental shifts.
Mm.
Individual behavior just gets overwhelmed by the collective flow.
Right.
And what starts as pressure can rapidly escalate into, well, violent, chaotic dynamics, leading to dangerous crowd crushes.
Here's the surprising thing, though. Despite the critical safety implications, understanding and predicting how these ultra-dense crowds behave has been notoriously difficult for researchers.
He really has.
Why? Because getting useful data from real-world scenarios is incredibly tough.
Mm.
We often only have access to low-quality CCTV footage where you can barely make out faces, let alone track individual people reliably.
Exactly. The signal-to-noise ratio is just terrible.
And the sheer complexity and chaos make traditional analysis methods just sort of break down.
Precisely. The data is noisy, and the dynamics are fundamentally different from lower density crowds where you might, model individual social forces. Existing approaches really hit walls.
What kind of approaches?
Well, you have empirical models that are somewhat understandable, explainable, but just not very accurate at high densities.
Okay.
Then you have powerful, data-driven deep learning methods. They can be accurate, sure, but they are black boxes. They predict the next frame, but you don't know why they predict it.
Right, no insight.
And they struggle to adapt if you change the environment or the crowd's goal. And most hybrid models, they also assume you can still track individuals, which, as you said, often isn't possible here.
So you're facing this kind of double whammy, messy, unusable data on the one hand, and incredibly complex, chaotic dynamics on the other. But what if, instead of trying to track individuals or just predict pixels, you looked at these crowds less like a collection of people and more like, well, like a physical substance?
That's the breakthrough idea in the research we're exploring today. This paper proposes a novel approach, analyzing and predicting extremely high-density crowds by seeing them through the lens of physics, specifically as active matter.
Active matter.
Yeah, instead of discrete agents, think of it as a continuous material made up of self-propelled particles that move collectively, exhibit internal stresses, and show, non-deterministic movement even under physical constraints.
Okay.
You see these fascinating phenomena like spatiotemporal fluctuations or waves propagating through dense crowds, much like you would in other active matter systems.
Active matter, I usually hear that term associated with flocks of birds or schools of fish, systems where simple individual rules lead to complex collective patterns.
What, like Toner 2 models and
Right.
things like that.
But people are different, aren't they? They can stop, they panic, they react to specific things. How does treating a crowd like a material or fluid really capture that human element, especially when things get chaotic?
That's a great question, and it really gets to the core challenge. While crowds share characteristics with other active matter, they aren't like water or simple materials. They have unique properties.
Ah,
The difficulty has been creating a physical parallel for dense crowds that isn't just theoretical, but one you can actually learn directly from that messy real-world video data.
Yeah.
Existing continuum models just weren't built for that.
Okay. So our mission in this deep dive is to understand how they built this learnable active matter model, what makes their crowd material unique, how it handles the data problem,
How it performs compared to existing methods.
and most importantly, what the simulation capability means for designing safer spaces and managing large events.
Right. Let's start by just reinforcing the scale of the challenge. As we said above, say 5 people per square meter, tracking individuals from typical low-quality CCTV is basically a non-starter.
It's just impossible.
The signal is weak, the noise is high. Traditional agent-based models that rely on individual trajectories are out.
And standard deep learning, while good at pattern recognition, like you said, gives you prediction without explanation.
Yeah.
If you widen an exit in real life, a deep learning model trained only on the old exit might not know how to react because it hasn't learned the underlying physics of flow, has it?
Exactly. It hasn't learned the why. This is where the active matter concept provides a potentially better framework. Dense crowds do behave like a continuous material in many ways. They flow, they compress, they exert pressure, they can even fracture sometimes.
Okay.
The key is building a learnable physics model that captures these specific crowd properties.
And that's where their proposed solution comes in, a new model that blends physics equations with neural networks. They call it a neurostochastic differential equation system. Bit of a mouthful.
Yeah. But the neural part
Mm.
means neural networks are learning key parameters within the physics model, making it adaptable to specific crowds and scenarios.
Okay, adaptable.
And stochastic captures the inherent randomness and unpredictability you see in active matter systems like crowds. I mean, not everyone moves in perfect lockstep, right? There's noise, individual decisions.
Makes sense. And the input this is clever. Instead of trying to identify and track blurry people, the model takes optical flow directly from the video frames. Just to clarify for the listener, optical flow is essentially a map of the apparent motion of pixels between consecutive video frames. It tells you which way things are generally moving in different parts of the image.
Even if you can't tell what is moving.
Right, and it's much easier to estimate from low-quality video than individual trajectories.
Precisely. That's a huge advantage.
Yeah.
Now, the model has several core ingredients. First, this crowd material model.
Okay.
The paper argues that crowd material isn't like simple water or elastic solids. It has unique, empirically observed properties.
Okay, what kind of unique properties are we talking about?
Well, properties like elastic asymmetry. Crowds are relatively easy to scatter or stretch out, but they're extremely difficult to compress beyond a certain point because fundamentally, people can't occupy the same space. You can't superimpose them.
Right, like trying to squeeze a bag full of marbles tighter and tighter, you hit a limit.
Exactly. And then there's exponential resistance. There's very little physical resistance when people are comfortably spaced. But as they get closer, the resistance to further compression increases dramatically, exponentially, until they are in full contact and become virtually incompressible.
Ah, okay. Exponential. And compression dominance, what's that?
That refers to how they resist being squished to compression much more strongly than they resist forces that cause shearing or rotation. Like people can tolerate some shuffling or side-by-side rubbing if it helps alleviate that intense compression pressure.
Okay, so the model needs to replicate these unique crowd physics. How do they actually build that in?
So they design a new material model that doesn't just apply to a grid, but models the strain-stress relationship between particles, essentially representing the forces between, let's say, notional individuals.
Between the marbles.
Kinda, yeah.
Yeah.
It specifically includes an exponential repulsive force that kicks in really strongly when particles get within a certain close range, that comfortable zone threshold.
Right.
And crucially, the parameters that define these material properties, like how compressible the crowd is,
Yeah.
similar to Young's modulus in traditional physics, and that factor K for exponential resistance, aren't fixed constants. They're learned by neural networks. And they can vary for different parts of the crowd at different times. So the material properties themselves become dynamic and adaptable.
Okay, that's the learnable part applied to the material itself. That's really interesting. But crowds aren't just passive material, are they? They have internal drivers. People want to move somewhere.
Right, exactly. And that's where the learnable active forces come in. Crowds have self-propelled motion and local actions deciding to push forward or stiffening their body or actively moving with their neighbors.
Yeah.
This manifests as an active force driving the collective motion. They model this drawing inspiration from concepts found in physics equations like the Toner-2 equation.
What now?
Toner-2. It's used to describe how individual units in active systems, like birds in a flock, coordinate their self-driven motion to create collective patterns.
So the bird flock equation applied to people flow. I love thinking about it that way.
Sort of, yeah. It includes components like motion alignment, the tendency for individuals to move in the direction of the overall flow, and a stochastic or random part to capture all those other individual variations and localized unpredictable actions.
Okay, the random jostling.
Exactly. And again, neural networks learn the parameters for that collective motion alignment. And the stochastic part is modeled using something called a conditional variational autoencoder, or CVAE. Think of a CVAE as a neural network structure, particularly good at learning the complex distribution of random pushes and pulls within the system. It learns the shape of the randomness, if you like.
Got it. And they also mentioned body forces as an option.
Yes, those are simpler global forces that can be added to guide the entire crowd, like a gravitational pull towards an exit, or maybe a centripetal force to simulate circular motion, like pilgrims walking around the Kaaba.
Okay. All right, so we have the unique crowd material model, the learnable active forces, and these optional global body forces. how do they actually connect this physics model to the optical flow data from the video? That seems like a key step.
It is. That's handled by the crowd MPM scheme. They use a framework called the material point method, or MPM.
MPM.
Yeah, it's a hybrid approach that combines two ways of looking at the system. It treats individual crowd members conceptually as Lagrangian particles.
Lagrangian, like following a specific point.
Exactly. Imagine tracking specific distinct points that carry properties like velocity and how much they're being squeezed or stretched. Like tracking a specific droplet of dye in a river.
Okay, yeah, I can picture that.
But it also uses a Eulerian grid, a fixed grid, over the space.
Eulerian, like measuring flow past a fixed point.
Right, like measuring the speed of water flowing past a fixed point in the river. The calculations, especially those related to the blurry optical flow data, are done on this grid.
Okay, why the hybrid? Why both?
This is crucial because it lets them learn from the grid-based optical flow data, which is Eulerian, while still modeling those particle-specific properties, like the unique material resistance or the local active forces applied to individual particles, which are Lagrangian.
Ah, bridging the gap.
Exactly. It also really helps smooth out the noise inherent in optical flow data. The process basically involves transferring particle properties to the grid. That's particle to grid or P2G.
Absolutely.
Doing physics calculations on the grid, grid operation or GEO, and then transferring the updated results back to the particles, bit to particle or G2P.
G2P, P2G, GO, G2P.
Right. This back and forth bridges the gap between the messy video data and the underlying particle physics model.
That makes a lot of sense, using the grid for the video input and calculations, but keeping the particle view for the distinct crowd dynamics. So theory sounds good. When they built this model, how did it actually perform when put to the test?
They use some really challenging real-world high-density data sets. I mean, these weren't easy lab setups.
Real stuff.
Yeah, we're talking real videos like pilgrims circling the Kaaba during Hajj, which is relatively peaceful but very dense.
Okay.
Concert goers in a wall of death scenario at Hellfest, very aggressive, chaotic.
Wow, yeah.
Runners in a marathon sort of flowing along a U-shaped road. And also controlled lab evacuation drills with different levels of urgency, peaceful, neutral, and aggressive.
And the densities.
High, really high, like 6 to 8 people per square meter in some of these.
That's truly high density. So what were the key measures of success? How did they judge it?
They primarily evaluated how well the model predicted the crowd's motion compared to the actual video, using metrics called Ervil and airflow.
Ervil and airflow.
Simply put, Ervil measures the difference, the error between the predicted underlying crowd velocity pattern and the actual velocity. Airflow measures the difference in the predicted pixel motion, the optical flow, compared to the real video's optical flow. Lower numbers mean better prediction accuracy.
Got it. Lower is better. And the results? How did it stack up?
Overall, their active matter model generally outperformed the adapted baseline methods they compared against. That included various other physics models and standard deep learning video prediction techniques.
Okay, generally better.
And this was particularly evident in predicting further into the future, what they call long horizon predictions.
Predicting more than just the very next frame.
Exactly. There were some nuances, though. For instance, one deep learning method called CVPR was slightly better on the Hajj dataset. Likely because the Hajj scene is a very calm, predictable, almost laminar flow. Simpler dynamics may be easier for a pure pattern recognizer.
Okay.
And sometimes in areas outside the main crowd flow in the marathon scene where the optical flow data was particularly noisy, pure data-driven methods might track that noise slightly better in the airflow metric.
Whereas this model smooths it.
Right. This model's physics structure tended to smooth it out, focusing more on the coherent crowd motion rather than the pixel-level noise, which you could argue is better for understanding the crowd itself.
Right. So better at capturing the actual meaningful crowd dynamics, especially the complex longer-term stuff, which is what you really care about for safety, isn't it?
I think so, yes.
Yeah.
And what about computational efficiency? That's often a big deal with these models.
Huge advantage there. Pure deep learning models for video prediction often require many input frames and have tens, even hundreds of millions of parameters. Massive models. This model, using only a single optical flow frame as input, achieved comparable or often better prediction accuracy with drastically fewer parameters, only about 3 million. Wow, that's a big difference.
Yeah, much more efficient to train and deploy. Also, because it's essentially a continuous time physics model, it doesn't rely on data being perfectly captured at fixed time intervals.
Good for messy real-world video.
Exactly. That's a major plus. They also showed it's quite robust to interruptions like missing frames and different types of input noise, Gaussian, uniform, mixed noise.
Why is it so robust?
Again, it's likely thanks to its underlying physics structure and that smoothing effect from the P2GGDP transfers in the MPM scheme. It's not just fitting pixels, it's fitting a physical process.
That robustness is essential if you want to use this in the real world, surely. Did they test how well it generalizes? Like, do behaviors or scenarios it hasn't explicitly seen before?
Yes, they did a cross-behavior test using those evacuation drill data sets. They trained the model only on the peaceful evacuation scenario.
Okay, just the calm one.
And then tested its prediction accuracy on the neutral and the aggressive version.
Wow.
As you might expect, performance did decline as the crowd behavior became more aggressive and less predictable.
Makes sense.
Yeah, it shows that predicting those highly chaotic, potentially panicky dynamics is inherently more challenging for generalization than calmer movement. The underlying rules might even be changing.
Okay, so it's effective and efficient at prediction, robust to real-world data issues. But the paper really emphasizes another major strength, its ability to be used as a simulator.
Yes. This is arguably the most powerful and unique aspect, setting it apart from pure black box deep learning. Because the model learns the underlying physics, the crowd's material properties and active forces. You can then use it to run simulations.
Right.
You can analyze behavior and explore what-if scenarios in virtual environments. This is absolutely critical for public safety and planning, where you obviously can't safely test dangerous changes in the real world.
That's huge. You can virtually experiment with potentially dangerous situations without anyone getting hurt. What kind of simulations did they actually demonstrate?
First, they showed how the model visually reproduces those unique crowd material properties.
Yeah.
We talked about the exponential resistance, the compression dominance.
How?
They ran a simulation of people being pushed into an enclosed area, and you can actually see phenomena like compression waves propagating through the simulated crowd. It behaves like the unique crowd material the model learned. Unlike standard physics models with fixed properties that would just act like a generic fluid or solid, you see the specific crowd behavior emerge.
So you can literally see the physics it learned in action. What else did they simulate?
They also demonstrated simulating the crowd behavior learned from one of those evacuation drill scenes and applying it to modified versions of that environment.
Okay, changing the layout.
Exactly. They simulated the crowd escaping through a wider exit and also escaping with a pillar placed strategically in front of the exit.
And did it predict the expected outcomes, like wider exit equals faster escape?
It did predict the intuitive outcome, that a wider exit reduces stress and pressure at the bottleneck. Makes sense.
Sure.
But more interestingly, it also replicated a sometimes counterintuitive observation from real-world crowd studies, that a well-placed obstacle, like a pillar, can sometimes actually reduce congestion and stress at an exit.
Really? How?
By helping to organize the flow into two more orderly streams rather than one chaotic bottleneck crush. The model captured that effect.
Wow.
This simulation capability is potentially invaluable for safety engineers and event planners trying to optimize layouts.
That's fascinating. Using a physics model learned from real data to confirm and even discover non-obvious safety improvements without risky real-world tests. They also mention analysis of the velocity field itself.
Yes, another benefit of having a physics-based model is you can analyze the predicted or simulated movement patterns using standard physics tools. They looked at the velocity field.
The flow pattern.
Right, and used operators like curl, which measures rotation or swirling motion.
That's vorticity?
Exactly, vorticity, and divergence, which measures expansion, where people are spreading out, or contraction, where they're aggregating or compressing.
And what did that reveal in their tests? What did they see?
In the evacuation simulations, analyzing the divergence clearly showed areas where the crowd was expanding as they moved towards the exit area, but also areas of strong negative divergence indicating aggregation and compression right at the bottleneck. You could pinpoint the crush point.
Okay.
And the curl analysis revealed swirling patterns near the exit when the flow was uneven, showing where rotational stress was building up, which can also be dangerous.
So it gives a much deeper understanding of why bottlenecks and dangerous conditions form than just looking at the raw pixel data or a simple prediction?
Absolutely. It provides interpretable physical insights.
Okay, that gives us a pretty comprehensive picture of this new approach. To recap quickly, it's a learnable physics model views extremely high-density crowds as this special active matter, uses optical flow directly as input, which is key,
Yep.
captures unique crowd material properties and these learnable active forces, leverages a hybrid particle grid system, the MPM, shows strong prediction performance, especially for complex long-term dynamics. It's efficient, it's robust to noise and missing data.
Right.
And crucially, provides this powerful simulation tool for analyzing scenarios and testing safety interventions virtually. That really does sound like a huge leap forward.
It is, potentially.
Yeah.
It provides a framework to move beyond just pattern recognition towards actually understanding the underlying dynamics, specifically for these really challenging high-density scenarios where other methods struggle.
But, no model is perfect. What are the limitations the paper acknowledges? Where does it fall short?
Yeah, they are quite clear about the scope. This model is specifically designed for extremely high-density crowds, generally above that 5 people per square meter threshold, and for large-scale movement dynamics.
Okay.
Different physics models, or maybe agent-based models, are probably still needed for lower densities, where individual choices and social interactions are more dominant. And this model doesn't really capture static or very slow cues well, though arguably those are less critical for immediate safety issues like crushes.
That distinction makes sense. What else? Any other limitations?
Well, the current model uses single-view video input. That limits its ability to generalize well to entirely different camera perspectives or, truly novel scenes it hasn't seen anything like before. Cross-view generalization is tough.
Right.
Also, it doesn't explicitly model some of the more complex micro-behaviors that can still occur, even at high densities. Things like people trying consciously to form small groups, specific queuing strategies, maybe lane formation, or detailed interactions with other elements like barriers or vehicles.
So it captures the bulk flow, but not those finer details.
Exactly. Incorporating those would likely require adding more complex forces or specific behavioral modules to the model.
And predicting a scene or crowd type it's never seen any data from. Still hard.
That remains the ultimate challenge for pretty much any model, including this one. While it showed it can generalize behavior learned in one scene to a modified version of that scene, like changing the exit width,
Yeah.
predicting entirely novel environments or crowd types with drastically different characteristics is still, an ongoing research problem.
So logical next steps would involve things like trying to incorporate data from multiple camera views, maybe adding modules for those more complex specific behaviors like queuing or grouping.
And definitely working towards better generalization to totally unseen scenes.
Right.
Those are the frontiers.
This has been a really fascinating deep dive, taking us from the potentially terrifying chaos of a super dense crowd to a novel scientific framework that helps us understand and potentially manage that chaos. It's quite something.
It really is.
Yeah.
By viewing crowds as this form of active matter and combining physics with machine learning, this research opens up genuinely new possibilities.
It really does shift the perspective, doesn't it? The seemingly unpredictable nature of these large, dense crowds might actually have underlying physical principles that we can model, learn, and leverage.
Yeah, that's the hope, that the chaos has structure we can understand.
And that brings us to the provocative thought for you, the listener, to take away from this deep dive. If we can now simulate dense crowd behavior with this level of detail, if we can really start to understand the impact of subtle changes like adjusting exit widths, adding obstacles, or even perhaps accounting for the collective mood of the crowd in the learned parameters, what are the broader implications? Could understanding the physics of crowds fundamentally change how we design everything from public plazas and stadiums to transportation hubs? Could this physical perspective be the key to making collective human movement significantly safer and maybe even more efficient in the future?